I welcome everyone to this video. I am Mr. Ish. Thank you for joining me. Let's look here at the concept of greatest curvature of a function. If you're looking at a function which is not a linear function, it has a curve to it, then you can determine or calculate the greatest curvature of that function. Very quickly, if I'm looking at a function such as x squared with a limited domain 0 to infinity, you know this right here, there's a certain curvature to this x squared. Where is the point of the greatest curvature of this function? Likewise, look here at this. You have the exponential function. There's a specific curvature involved. Where will you see that greatest curvature of this? We'll be looking over here at this function for this video, the natural log x. It looks something like this. The natural log x has a certain curvature, but there's a point at which that curvature is the max. How can we determine that greatest curvature? That is the essence of this video. This right here represents the derivative applications of geometry, and that's what we're looking at over here, and it makes for an interesting topic. The best way to understand this is by means of an example, but very quickly look over here. The curvature, which is symbolized with a capital K of a curve, is your rate of change in the direction per unit of arc length of that function. Or in other words, you can say the rate of change of the angle of inclination of a tangent at a point on that function per unit of arc length. You can understand this by means of a graphic representation. If I'm looking at a graph of a function which looks something like this, I specifically pick a point and I'll call that point P. If I were to draw a tangent line at this point on this function to this point, I'm drawing a tangent line. Your tangent line would look something like this. I'm obviously using my free hand here, so there will be some inconsistencies, but there's a specific angle involved. We'll call that angle A. If I were to move at a specific point, I'll call that point Q, and I were to draw, and remember this is a point P and a Q on the same function. I've now picked a second point. I draw a new tangent line at this point. You're looking at a tangent which develops like this. Obviously, you know, because you've changed your point on that function, on the curvature of this function, you have a specifically different angle. That angle will be equal to a new angle, or you can represent it as this. We'll call it A2, but A2 could have been equal to your original angle A plus a change in that angle A. If you were to look at the angles of these two tangent lines, you see this tangent line is coming out over here and it continues right over here. This other tangent line came over here and it continues over here. The difference of these two right here, that right here would be delta A. Now I'm only showing you this because I'm trying to give you a visual example of what this part right here represents. You're looking at the rate of change in the angle of inclination of a tangent at a point per unit of arc length. What does this per unit of arc length mean? You're going from point P to point Q on a specific arc because this function is curved, and that right there, the area between P and Q, there's a certain delta S. That's your change in your arc length. Per unit of arc length, you have a specific change in that angle, and that change in angle is delta A with regards to two tangent lines you drew at two different points, P and Q, but you're seeing it. This right here helps you understand the formula which comes about for determining the greatest curvature. We're not deriving the formula, but I'm showing you the formula. The formula to determine your greatest curvature depends on this specific calculation coming through. K is equal to a d squared y over a dx squared. You know this is your second order derivative of your function divided by 1 plus your first order derivative of that function. You're going to look at this first order derivative here with the square, and then all of this to the power of 3 over 2. This right here is giving you your value of k, your curvature of your function. But to determine the greatest curvature of that function, you're going to send this through a derivative procedure, and we'll just call this a DTV. You'll send this k value, your outcome from this formula, through a derivative procedure. That derivative procedure will give you your point for your greatest curvature. Your greatest curvature for a specific function will have a certain x and a y value, and that x and y value will be determined from the derivative of this k function, which we will develop. And we are looking here at a natural log x function. But look, I told you at the very beginning, the best way to understand this concept is by means of an example, so that is the route we will take. This concept is not difficult. The most tedious part, or the difficult aspect of this specific greatest curvature calculation, is this. Once you've determined this k, which will be indeed a function representation, to determine the derivative of this, it can be cumbersome because you're going to be using the quotient rule. Depending on your original function, the quotient rule calculation can become quite complex. But I told you already, my f here, which is equal to my y, my function is equal to natural log x. And I know my first order derivative, which is my y prime of this natural log x, is 1 over x. I know my second order derivative, which is my y double prime, is the derivative of 1 over x. You know that to be minus 1 over x squared. Look, I have a representation here d square y over dx squared. This right here is equal to d square y over dx squared. This right here y prime is equal to dy over dx. These are just different ways of representing the same thing. This k formula can also be modified to be represented with regards to another variable, and that representation would then change to this. You'll have a d square x over dy square, but that's not what we're looking at here in this video. This is just me showing this to you. Dx over dy, and this right here would be a square to the power of 3 over 2. Look at the difference between these two. Both of these are giving you your k values which are involved in your greatest curvature calculation, but the k here indicates the curvature of your function. But look, here you're looking at a derivative with respect to y, here you're looking at a derivative with respect to x. The differences are apparent for you. The focus of this video is going to be involving the derivatives with respect to y. Anyhow, we digressed where let's get back to our original calculation. I told you the hardest point is once you've determined the k to do the derivative, but we haven't determined the k, but we can. We have everything now to determine the curvature of our function. K is equal to my second order derivative, which you know this, minus 1 over x squared, divided by this calculation coming through, 1 plus my first order derivative, which is 1 over x, but you know that's a square. And then you know all of this is to the power of 3 over 2. Now you have to send this to its algebraic calculation. I'm erasing this because you don't need to see this formula anymore. I've used this formula. The only next part is now to do the derivative of our k, and we will. When the time comes, we'll do it. We'll erase this entirely. Now we have to algebraically manipulate this, meaning we have to solve this out to the greatest extent possible. So when we do the derivative by quotient rule, we have less work. We have to manipulate all of this. I have minus 1 over x squared in the numerator, and in the denominator, what do I have? I'll look at this. I have a 1 plus 1 over x squared all to the power of 3 over 2. Look here, only in this area right here, you can do fraction algebra. Common denominator here will be x squared. That will become an x squared plus 1. When you clean this out, what are you looking at? I'm going to clean this out properly for you so you see everything come through. You have x squared plus 1 over x squared all to the power of 3 over 2. And you know there's nothing wrong here. You have a 1 over x squared, you do fraction algebra, you have x squared plus 1 over this. Now use your laws of exponents to separate the numerator and denominator into individual exponents. It's no different than you saying a over b to the power of m is equal to a to the power of m over b to the power of m. Laws of exponents, you'll separate it out. That's what I'm doing. When I separate it out, this is what I have. I have x plus 1 to the power of 3 over 2. Then I have x squared to the power of 3 over 2. And let's do it. I have x plus 1 to the power of 3 over 2. And then I have here an x squared to the power of 3 over 2. But this x squared to the power of 3 over 2 can be simplified because these cancel out. You are left here with an x cubed. When you simplify this here in the denominator, you have an x cubed. I know I'm erasing and writing, but this right here is nothing other than algebra and laws of exponents. I've ended up here with x cubed. And you can say you're going to flip the fraction around. You'll have here a minus 1 over x squared, that's this numerator, times this x cubed over x squared plus 1 to the power of 3 over 2. Remember, all of this right here is still equal to k. We haven't done the derivative of it. We have to do it. You'll clean this out. You'll simplify it. This cancels out with that. I'm left here with the k value, which is a minus x over x squared plus 1 to the power of 3 over 2. And that right here is equal to k. This right here I'm erasing is all the algebra which came into play. You see the k value right here clearly right over here. We simplified by means of algebra to arrive right over here, and it's correct. My simplified k value, which represents the curvature of the function natural log x, is defined by this minus x over x squared plus 1 to the power of 3 over 2. It's a function, but it defines the curvature of this natural log x. Now I have to determine the derivative of k. What I've done here is make room for our most difficult calculation here for the greatest curvature exercise. We've arrived here at the value of k, which represents the curvature of your function. We know our original function was natural log x. You don't need to see the first and the second order derivatives anymore. We already used them to arrive here at this. By means of simplification, we came over here. What we need to do is determine the derivative of this k, the derivative of your curvature, which you can represent as this, dk over dx. What is this? You'll do this by means of a quotient rule. You're seeing here an f function, and you're seeing over here a g function. You know the quotient rule. You have to run this through. You have a g function times the f function derivative minus the f times the g function derivative divided by the g function square. And you know you're looking at a g function, which is a composite function, so you'll have a chain rule come into play in addition to your quotient rule. So run everything here through this rule, and let's see. You're looking at a g function times the f function derivative. I have a x squared plus 1 to the power of 3 over 2 times the derivative of minus x, which is a minus 1. And then the minus from your quotient rule, you have your f function, which is minus x, times the g function derivative of this. You know your g function is equal to x squared plus 1 to the power of 3 over 2. If you do a u substitution, u is equal to x squared plus 1, then you know the g function with regards to u is equal to u to the power of 3 over 2. You have to do the chain rule here. The derivative of u with respect to your g variable is what? It's u to the power of 3 over 2. You'll do the derivative of this. Then you'll do the g variable with respect to the x variable. You do x squared plus 1. Now let's bring those items here. This right here is where all of this will come in too. The derivative over here is going to be by means of the power rule. You know x to the power of n is equal to n times x to the power of n minus 1. You'll have here a 3 over 2 u to the power of 1 over 2 because the exponent reduced by 1. The derivative over here is going to be a 2x. This right here is the chain rule coming through, and we've used it and we're good. Now we're looking at the denominator item. The denominator item is just g squared. You're going to square your entire denominator. You take this to the power of 3 over 2 and you square it, you'll have it to the power of 3. You have an exponent 3 over 2, you square it, these cancel out, you have an exponent 3. You're looking at x squared plus 1 to the power of 3. That represents your g squared, and you're good. Now you have to simplify the numerator. Look right here, minus 1 with that, I'm looking here at a minus x squared plus 1 to the power of 3 over 2. This minus will become a positive. This denominator 2 and numerator 2 will cancel out. I have a x times 3. I'll have here a 3x squared times u to the power of 1 over 2. You know u was equal to x squared plus 1 to the power of 1 over 2 divided by your denominator g squared was x squared plus 1. Remember, what we're doing now is taking the curvature, the k, and doing the derivative by means of the quotient rule. We happen to have a chain rule come through, but we're just simplifying that entire irrational expression. You're going to isolate here in the numerator an x squared plus 1 to the power of 1 over 2. When you isolate it, it comes in here 3x squared times, and it comes in here minus x squared plus 1 times. Because you're looking at 1 over 2 and 3 over 2, the difference of that is just 1. 3 over 2 minus 1 over 2 is a 2 over 2, which is here an exponent 1, and it makes sense, divided by g squared, which is x squared plus 1 to the power of 3. You can simplify the item you isolated. This x squared plus 1 to the power of 1 over 2 can simplify with this. You have x squared plus 1, x squared plus 1, you have a 1 over 2 and 3, you'll do a 3 minus 1 over 2, which will be a 5 over 2, which is a 2.5, and it makes sense. I'm looking at x squared plus 1 now to the power of 5 over 2. This is just simplifying your items with the same basis, but the exponents subtract or add based on your laws of exponents. This is what I have. We'll take this to our completion. Right here is going to be what? We'll bring in our derivative right here. In the numerator, I'm looking at a 3x squared minus x squared minus 1, which will be a 2x squared minus 1 in the numerator. Look, you're just looking at this part. 3x squared minus x squared minus 1, 2x squared minus 1. In the denominator, I have a x squared plus 1 to the power of 5 over 2. And here is my end result. I determined the curvature, now the derivative of that curvature, and that right there is a function, and we'll use that to determine our point of greatest curvature, a certain x comma y value. That right there is easy. How do you determine that point of greatest curvature? It's like this. You have a certain k derivative, which is indeed a function. You're equaling it to 0 and you're solving for that x value. And how will we do it? Well, we have our function, equal it to 0 and solve for x. I have here a 2x squared minus 1 over x squared plus 1 to the power of 5 over 2 is equal to 0. You push this on the other side, it zeroes out. I have a 2x squared minus 1 is equal to 0. 2x squared is equal to 1 and x squared is equal to 1 over 2. X squared is equal to 1 over 2 and x here is equal to plus and minus 1 over root 2. You're solving for x. But I'm going to throw out the negative value. I know now x is unequal to 1 over root 2. Why am I throwing out the negative value? Because your natural log is not defined for negative values. It's only defined for positive values. Otherwise, both values would be fine. Here is our true answer, 1 over root 2. This right here is indeed a critical point. You've determined the critical point x value. Now you have to determine the critical point y value by putting into your original equation function and solving for it. I have my x value. What is my y value? Let's do it. You took your derivative of k, you solve for x, you throw out the negative because you're looking at a natural log, you retain the positive value and you work with that. It's a critical point x value. My critical point y value is going to be what? Y is equal to natural log of 1 over root 2. This can serve as your answer, or you can simplify it. I'm using what properties of logs. Natural log 1 minus natural log root 2. I have a common log with the quotient. It's independent logs of the difference. This is a 0 minus natural log 2 to the power of 1 over 2. You know root 2 is a 2 to the power of 1 over 2. You can bring in your properties of logs. I have minus 1 over 2 and natural log 2. And here is my y value. My critical point y value is equal to minus 1 over 2 natural log 2. What is my point of greatest curvature of natural log x? I know it now. It's a 1 over root 2 comma minus 1 over 2 natural log 2. And here is the correct answer, and it will be it. We've determined it. Our curvature, derivative of curvature, from that function you determine your x value, from your original function you determine your y value. Here it is, and it's correct. What does this mean graphically? I'll show it to you, and that will be our end of our video. I'm looking at a natural log x function. 1 comma 0 is my x-intercept. I'm looking at a function which looks something like this. You would have to graph this 1 over root 2 comma minus 1 over 2 natural log 2. 1 over root 2 is less than that. You're looking at a point somewhere over here. In this area right here, your natural log would have the greatest curvature. The function will experience its greatest rate of change, and you've determined it, and it's correct. And that right there brings us to the end of this video. Thank you for watching.